Section 7 is called inverse relations and functions. Inverse relations are not reciprocal relations. These are two completely different things. You guys kind of did inverse relations back in geometry, and this is your official introduction into them. An inverse relation simply switches the x and y coordinates for every point in the relation. So I'm going to go back to geometry here to show you what an inverse relation does. We're going to graph a figure formed by these three ordered pairs. If I have three ordered pairs and I'm making a figure, what will the figure look like probably? Yeah, it's going to be a triangle. So we're graphing a triangle here on this grid. And then we'll graph the inverse relation. So first, I'm going to plot each of these three ordered pairs and label them. So -3, +2 is there, and that's point A. 0, 1 is here, and that's point B. And then 3, 4 is here, and that's point C. Now I'm going to go ahead and draw in the figure because the figure itself is kind of an important thing so that you can understand the concept of what these inverse relations are that we're working with in this section. Yes, when you do geometric transformations and you're using original points and then some sort of transformed point, we use the label prime. So we need to figure out what A prime is going to be. To do the inverse relation, we swap the x and the y coordinates. So for point A, we trade the x and y, and we get A prime, which is 2, -3. So then B prime is what? 1, 0, and C prime is what? 4, 3. Okay, so let's go ahead and draw in those ordered pairs. We have 2, -3, and that's A prime. We have 1, 0, that's B prime. And then 4, 3, and that's C prime. And then also draw in the shape. Well, I'm going to ask you that here in a second. So what do you notice? Let me get rid of that. What do you notice? What? It is like a reflection over what? A diagonal line. What is the equation for that diagonal line? Y equals 1 is a horizontal line that goes through 1 on the y-axis. Y equals x is the correct equation. So if I were to draw in a dotted line here, do you see that it looks like the blue figure was reflected into that dotted line and then you see its image on the other side? Okay. That dotted line is the line y equals x. And what we can say from what we just found is that if I find an inverse relation, its graph will be reflected in the line y equals x. This is always true for every inverse relation. It actually is a reflection in the line y equals x. Okay, so that was an inverse relation. This is an inverse function. The formal function notation for an inverse function, unfortunately, looks like that. Why do I say unfortunately? Yeah, we have a negative exponent looking thing right here. It looks like this says f to the negative first power. But that's not what it actually says. This is the formal notation for an inverse function. This is read f inverse of x, not f to the negative first power. So please make sure you're trying to read that correctly in your head every time, and then you won't make that mistake. Because if I think of this as f to the negative first power, a negative exponent tells me to move something to the denominator. And the classic mistake that people make is they think that, and then they do something like this. They put 1 over the function. And that is not the inverse function. That is the reciprocal, and they are completely different things. This is not 1 over x. So think of this in your mind as f inverse, or the inverse of f. of x. Okay? Now, just like with the previous page, all we have to do is switch the x and the y coordinates. So if f of a equals b, just whatever number equals whatever number, to find f inverse, just switch the coordinates. And it gives you f inverse at b equals a. That's the notation that we're using here. So notation can be confusing. Please try to understand it, because when you see it, then you'll understand what it is that it's saying. So read it correctly in your mind, learn what this language is that it's trying to get you to say, and then hopefully you won't be confused. To find the inverse function, rewrite the function in terms of y. If they give you function notation, f of x equals something, then you want to change that f of x into just y. That's the easy way to do this. Then swap the x and the y coordinate, or the x and the y variables in the equation. And then resolve the equation for y. And then if they ask you to graph it, go ahead and graph it. So basically, write y equals the equation, swap the x and the y, so then you have x equals the equation, and then solve for y. So in this right here, we can graph this right now. Let's go ahead and do that. This is just a line, f of x equals 2x minus 5. My y-intercept is all the way down here at negative 5, a slope of 2. So I go up 2 from negative 5 to negative 3 over 1. And then I go up 2 from negative 3, so here over 1. There's my first dot. And then a slope of 2 each time. And I can draw on that line. You can graph a line using the y-intercept even if the y-intercept isn't on the page. You just have to think a little bit, apply the slope until you get back on the graph. Okay, to find the inverse function now, we're going to trade the f of x and turn it into y. Y equals 2x minus 5. We do that just because it's a little bit easier to work with. And now we're going to swap the x and the y variables. So that becomes x equals 2y minus 5. Now we have the inverse function, we just have to solve for y so we can graph it. So to solve this for y, I'm going to add 5 to both sides. And that gives me x plus 5 equals 2y. We're basically just back in Algebra 1 right now. Solve for y, so divide everything by 2. And I get y equals 1/2 x plus 5/2. So that's the equation for my inverse function. I can put that back in function notation if I want to. I can turn that y back into f of x. So I'd write f inverse, since that's my inverse function, of x equals 1/2 x plus 5/2. That's the equation that I need. That's my inverse function right there. So if the problem asks me to find the inverse function, that's how you do it. Swap the f of x for y, trade the y and the x, solve for y, turn it back into function notation. F inverse of x equals this. Now let's graph it. And we should see, just like we saw with those triangles, we should see a reflection in the line y equals x. To graph this one, we have a y-intercept of 5/2, which is the same as 2 1/2. So here's 2, here's 2 1/2 right there. I got a little tick mark that I can actually put this on. And then we have a slope of 1/2, so that means I go up 1, right 2, up 1, right 2, up 1, right 2. Or I can go down 1, left 2. So I got all those dots in there, drawing the line. Just like we're back in Algebra 1. And does it look like we have a reflection in the line y equals x? If I draw in that line y equals x, it'll be basically like this. And there it is. You can clearly see that our inverse function is sort of a reflection of the original function in this line. What was here is now here, same distance away. What was here is now here. What was here is now here, and so on. Okay? So the inverse function makes a reflection in your graph along the line y equals x. To find it, swap the x and the y, solve for y, and you have your inverse function.